Hello, I'm Bryan Wakefield, and I'm going to talk to you about the projects that are available in my group this summer for the SCORE program. We're going to be looking at the synthesis of natural product analogs. Natural products are an important source of compounds that become drugs. They are often leads to drugs. We find a natural product that does something, we then work on its structure, try to make it better, and then it can be used as a drug in clinic. So we have things like artemisinin, which is an anti-malarial that is just used as it is found in nature. Then you have codeine, oxycodone, or OxyContin that are modified opioids that can be used in the clinic as well. But these compounds are changed from their natural compound. So that is our hope here, is to look at either the phydianidines or flinderol C and try to make analogs of them, make derivatives to see if we can better understand and improve their biological activity. So the phydianidines are selective for the mu opioid receptor, which is interesting with the opioid crisis. Having compounds that are selective for the mu opioid receptor is rare. And analogs of this compound have been found to be neuroprotective against oxidative damage. And then the flinderols are compounds that are derived from a plant that have been shown to have anti-malarial activity against a few different strains of the P. falciparum parasite that causes malaria. So making improvements on these compounds could help us make better drugs in the future. So a while back, Jung and co-workers reported analogs of the phydianidines. And what they had done is the section in white here, they replaced with an aromatic ring. So you can see in this structure, that long straight chain has been replaced by two rings. And what they found was that by replacing that long chain with this furan and benzene ring, they were able to make compounds that were protective against oxidative damage in nerve cells, which is important for the to prevent or treat the onset of dementia. So what are we trying to do? We look at the molecule as kind of having three sections. This purple section, which is the indole, the yellow section, which is the central aromatic ring, and then that white section with the two rings. And going through the literature, a thing that has not really been done is changing that purple section. The way people make the molecules does not really allow them to make changes at that ring. So we wanted to come up with a way where we could install that purple ring at the very end of the synthesis. And then people haven't looked at what happens if you change that central aromatic ring, which is called an oxidizole, to something else. We want to systematically change that ring and see which of the atoms in that ring, oxygens and nitrogens, matter for biological activity. So I'll save you all the nitty-gritty chemistry details, but we were able to replace the central oxidizole ring with a furan. So we were able to go through the synthesis, make the alcohol that we need, so second line, far right-hand side, and then we found conditions that allowed us to add indole to that alcohol and make the analogs. Over the summer, students are going to construct the alcohols, that OH compound, and work on adding the indole to those alcohols with different aromatic groups, the ones highlighted in yellow below. And then we're going to optimize the indole addition, which just basically means finding the best possible conditions so we get the highest yield of these reactions. And then we're going to use these conditions to add indoles of different structures to these alcohols to make a whole bunch of different compounds. And then we're going to supply those compounds to biological collaborators who can test them to see which ones are good or which ones elicit the biological activity that we want. The other project is the synthesis of flinderol or flinderol C. We look at this molecule as kind of having three unique regions. In this case, the indole is yellow, the double bond that is red, and then the groups coming off nitrogen that are blue. So we want to try to figure out ways to simplify the structure and then look at all of these different areas of the molecule to figure out which are important for biological activity. So towards this end, in the past, we've been able to make kind of the core of the flinderols, the 3 rings, um, in like moderate yield, but this compound wasn't fully functionalized. We were missing a carbon chain on it. So we've gone in and we've tried to add this carbon chain. And over last summer, the high school student that worked with me, Kirsten Watts, um, improved this second step in the sequence where we have to add this CO2Me group. And Anna Pettijohn and Claire Romaine have been working on trying to find good conditions to add an allyl group to that so we can then work on cyclizing the molecule. So over the summer, what this project kind of has to it is first optimizing the allylation, so just finding good conditions to put the allyl group on, and then optimizing the metathesis, which is adding that alcohol group, and then finally trying to find the right conditions, either BF3 etherate or the boronic acid that we use in the phytoanidine project to affect the ring closure and make this tricyclic core that you see at the bottom that has all the functional groups that we need for phytoanidine. So I'm hoping that we'll be able to do that relatively quickly and move the project forward. So I hope I've shown you 2 interesting projects with phytoanidine and the flinderols that allow students to use organic chemistry to try to make molecules that are of biological interest. And either project that you find interesting or appealing, I'd be willing to work on this summer. So it's really up to you as to which project you'd want to do. And these projects have been supported by the College of Science, Coast Carolina University, the Department of Chemistry paid for a student, Anna Pettijohn, to work on the flinderols, and the WeSTEM program paid for Hannah Higgins to work on phytoanidine. And then the SC Embry program has supported us over the years as well.